slowly now. So hello everyone to the next N3AS seminar. And today's speaker is Dake Zhou, who got his PhD at the University of Washington. And now he's one of the N3AS Physics Frontier Center Fellows. So Dake will talk today about dark lepton superfluid in proto-neutron stars. Go ahead, Dake.
Right. Thanks, Anna, for the introduction. So unfortunately, I cannot see anybody on my screen since I'm at full screen. So please feel free to interrupt me if you have any questions, or I will be happy to answer those at the end of the talk. This work, so this topic is based on my recent work with Sanjay, with archive number, in which we studied how a new scalars that couples with neutrinos could form a new phase of matter in proto-neutron stars. I found this topic very interesting, and we're actually constantly updating our knowledge around this new phase of matter. So I'm very excited to tell you about our work. So let me start by briefly review the relevant astrophysics of proto-neutron stars. They are the remnant of core collapse supernova, and they're formed when the central density of the collapsing stellar core reaches about a few times the nuclear saturation density in naught, where in naught equal to 0.16 inverse Fermi cube is the typical density of nuclei. So at this stage, the star has a size about 20 or 30 kilometers, and they're characterized by the core temperature around 20 MeV. So in this hot and dense environment, neutrinos of all flavors and both helicities are produced in abundance. Subsequent to their production, those neutrinos are actually trapped in this environment, and they can only leave the star through diffusion, which takes about 20 seconds. The trapping of the electron flavor in particular would sustain a very large lepton chemical potential that can be as high as 200 MeV at the center of the star. And the gradient of this chemical potential drives the neutrino diffusion, and during this during about this 15 seconds, the diffusion generates heat and further heats up the star to reach a core temperature as high as about 50 MeV. Simulations suggest that neutrinos are not only important in the dynamics of core collapse, but also important in the evolution of proto-neutron stars. And in fact, they carries away about 99% of the total energy released during the core collapse. So it is quite amazing that neutrinos, which almost behave like a dark component, at least in terrestrial laboratories, can play such a huge role in astrophysics. So all these extreme environments, the high density, the high temperature, as I will show, to be a very important ingredient in this work, a very high lepton number chemical potential make proto-neutron stars very unique laboratories. Before moving on, I would like to emphasize that actually similar conditions could be achieved in bioneutron star mergers, given that provided that the remnant does not fall to a black hole immediately. But just to be concrete, I will focus on proto-neutron stars in this talk. In fact, people already use this laboratory to study dark matter, and there's a large category of work that belongs to this supernova cooling bound on light dark matter. The general idea is that new light particles with mass less than, say, about the temperature of the proto-neutron star can escape the star and efficiently cool the star, which could reduce the duration of neutrino signals we expected from a core collapse supernova. So fortunately, we observe about 20 neutrinos from the supernova 1987, whose spectrum are plotted here. So if the temperature drops too fast, we probably wouldn't see a neutrino signal that lasts that long. And these 20 neutrinos, although only a small number, proves to be a very important tool in putting constraints on a large class of dark particles. So schematically, let's call the coupling between the dark matter and the standard model to be G, as plotted on the horizontal axis here. And very small g's, some of the light dark particles will be produced in abundance, and they will simply leave the star, carry away some of the energy. So as we increase this coupling, more particles are produced and carrying away more energies at a higher rate. As that is the luminosity, which is plotted on the y-axis, start to increase. But as we keep increasing in this coupling G, the particles produced will be trapped by the star, very similar to neutrinos. So eventually, at some point, the emission becomes, the emission only comes from a decoupling surface, again, very analogous to neutrinos. So the luminosity does not start to curve down. And as the coupling keep increasing, the decoupling surface are extended to a larger radii or a smaller temperature, so the luminosity start to decrease. A simulation by earlier works in earlier work suggests that if the dark matter luminosity exceeds that of the neutrino, we probably won't be able to see a 20 seconds long neutrino signal. So this, known as the cooling bound, has already put lots of constraints on say, stereo neutrinos or axions, those light species. But what has not been studied carefully is this trapping regime, where the coupling is really strong and the luminosity bound no longer applies. And the work I'm going to talk about today is actually one direction is one project in this direction. And in this work, we specifically look into dark particle scalars that couple to neutrinos, because such models are quite well motivated. On the theory frontier, we know that the standard model right now is insufficient to explain all the neutrino phenomenology. For example, the oscillation data tells us neutrino have masses, but whether is a simple Dirac origin or Majorana, or maybe a combination, is currently unknown. And there are also lots of hints from laboratories and from the sky. So in addition to this long-standing short baseline neutrino anomalies, there has been lots of attention surrounding this Hubble tension and its potential solution resulting in strong neutrino self interactions. It's a very heated topic, so I will present a sort of simplified version of this story, just to create some context. So this Hubble tension refers to the discrepancy between the inferred value of the Hubble constant from those from CMB and those inferred from the cosmic distance lidar, with the former is about 10% less than the latter. So this discrepancy started to show up since the first release of Planck data, maybe half a decade ago, and the tension has since grown gradually, and right now is probably at a 4 sigma level. So these all these local measurements are quite sensitive to, probably quite sensitive to the astrophysics of our local cluster. The CMB physics is more depends on a wider range of the cosmic evolution epoch, before the CMB and after. So the general consensus is that if this tension is true, then there probably is probably more likely that there are some new physics or modified cosmology that can bring the CMB inferred value closer to the local measurement. There actually is there is one solution that has been known for quite a while, and that is based on this degenerate effect among the CMB parameters when doing the fit. And this one is about the correlation between H0 and N effective, the effective number of relativistic species around CMB time. So as we can see, if we just assume a standard model in effective around 3, the center of the centroid of this Planck inferred value is quite deviates quite a lot from this gray and black band, which are the local measured values. But we can extend this trend towards a large delta N effective, say equal to 1, then the center is sort of overlapped. So that's a sort of simplified version, but that's an hint on how one can resolve this tension. But the issue is we cannot just arbitrarily vary this ineffective because if we increase the number of relativistic species, there will be an enhanced damping on the small scale matter density fluctuations. And this is where the neutrino self-inaction came into play. And so neutrinos, as being a relativistic species before CMB, has similar suppression effect, damping effect on the small scale structure. So if their free streaming can be suppressed by some new interactions, then the effect of increasing ineffective can be compensated by these new interactions. Then the question is, how strong does that interaction has to be to accommodate a delta N effective about on the order of 1? And the answer is that the interaction has to be very strong. And so in the plot, in these two plots, in this second plot shown here, which is called the moderate interacting neutrinos, these authors consider a effective 4 fermion coupling about 1 million times that of the Fermi constant, or even in a stronger version, they consider effective coupling about 10 to the 9 times G Fermi. Yeah, it is noteworthy that the Hubble inferred Hubble constant H0, which is plotted on the horizontal axis, are indeed pushed or shift towards a larger value that is more consistent with those local measurement as compared to just the standard lambda CDM cosmology. Yeah, but the bands are also broadened because right now there's a new parameter that can accommodate more freedom. But what's really makes this solution very promising, or at least to those guys, is that they found that there's these two scenarios not only alleviate this Hubble tension, but also simultaneously alleviate this another tension surrounding sigma 8, which characterizes the matter density fluctuation around about at 8 megaparsec, which is plotted on the vertical axis. So in both cases, the posterior of the cosmology with interacting neutrinos are pushed downwards to values that are locally measured as compared to a larger perturbation as suggested inferred from the standard lambda CDM cosmology. And this is mostly because there are lots of their degeneracy because they use sort of degeneracies and the correlations among mainly the sum of neutrino masses and effective and these effective four-fermi uncoupling, and they find that by allowing a very large strong coupling and also increase the sum of the neutrino masses, they can simultaneously alleviate this two tension. And so again, this is quite a, well, there's a lot to talk about it. It probably would be another seminar. And so and either of these claims are probably suffer some unknown systematics. But the bottom line is that there are indeed a good motivations to consider light as mediators that couples light new degrees of freedom that couples to neutrinos, because as a simple estimate reveals, to get something as strong as 10 million, a million times the G Fermi, the natural scale that one expects for the mediator will be on the order of 100 MeV. And as discussed earlier, that's a range that is very interesting to proto-neutron stars. So in this work, we consider a very specific particle model. That is, it contains a new gauge neutral scalar phi that carries 2 units of lepton number. It has a mass m phi and is characterized by a quartic coupling lambda. It couples to the active neutrinos of 3 flavors through this coupling G. Although this term violates the standard model gauge group, it can be generated from dimension 6 operator shown below. So the L, the capital L denotes the standard model lepton doublet. And as the Higgs develops a wave after the electroweak symmetry breaking, this coupling to the flip Higgs doublet will make sure that we will get a neutrino only coupling and show in the in this effective Lagrangian. Such model has been studied extensively in the literature, including N3AS collaborators Andre and Jeffrey, and that's because this this operator, effective operator, essentially obtained by composing the dimension 5 Weinberg operator to a new scalar. The UV completion of such model is almost identical. It's very similar to that of seesaw models, and again has been studied extensively. But the bottom line is that there are well-motivated models that would naturally give rise a large coupling, a G of order 1. So this makes this model very interesting to phenomenology. There are, however, constraints from other sources, such as laboratories and the early universe. To begin with, it is well known that light relativistic species during BBN could accelerate the expansion history, therefore spoil the predictions of standard BBN. So to avoid this constraint, we sort of we focus on M5 heavier than about 10 MeV. I want to mention that this due to its direct coupling to the active neutrinos, the BBN constraint on the phis can actually be somewhat different from those that performed earlier. And to my knowledge, there hasn't been a fully consistent study of this issue. And indeed, the actual BBN constraint is an ongoing work that is related to this project. So on the heavy side, we also require that the M5 to be less than about 300 MeV, so that they can be produced in the supernova. This is somewhat larger than what one would naturally expect from a thermal production point of view, and this is because of the finite lepton number chemical potential, as I will discuss in more detail on the next slide. So in this mass range, the relevant laboratory constraint mainly come from exotic count decays, which requires the coupling, the diagonal coupling to the electron favor GE to be less than about 10 to the minus 2. In this talk, I will only focus on this diagonal coupling. and I will comment on possible roles of other couplings in the concluding slide. And the one final possible constraint coming from the cooling bound I mentioned earlier, and back of the envelope estimate suggests that GE larger than about 10 to the minus 6 should be sufficient to make sure that the cooling bound is not violated. Now, what does the scalar do in the supernova? So as discussed earlier, for a weak scale, for a new weak scale interaction, the particles can be easily produced in abundance and brought into equilibrium in the star, as revealed by its production rate and its short mean-free paths. So in this in equilibrium, the scalars are sourced by its chemical potential, which is equal to twice that of neutrinos, simply because it carries 2 units of lepton number. Because nu L can be as high as about 100 to 200 MeV, this allows us to consider massive phi's as high as 300 or 400 MeV, as I explained on the last slide. As bosons, the scalars will condense when their chemical potential exceeds the rest mass m phi, as is evident from their effective potential, because it will develop a maximum height shape when mu is greater than m. So in this potential, the finite vacuum excitation value of scalar would spontaneously break the global lepton number symmetry, and the flat direction corresponding to the Gaussian mode suggests that the ground state is a lepton number superfluid. So as well, one may know that the superfluid, such as the superfluid helium, is known to have a dissipation to display dissipationless supercurrents that are very efficient in transport, and that is indeed what we find in the context of a proto-neutron star. One of the most striking feature is that we find the superfluid can almost transport lepton number instantaneously. So in the standard scenario, as I discussed earlier, a finite lepton number chemical potential and its gradient, as shown in the plot at the top, drives the neutrino diffusion, which takes about 20 seconds. But in a superfluid, the chemical potential has to be almost a constant, as shown in the green curve. This in turn suggests that the lepton numbers are efficiently transported from the center of the star to the surface. This is shown at the bottom panel. So the dashed lines are the standard scenario with a chemical potential given by the orange curve above. As we can see that at the center, both lepton and electron fractions are about a third, and it decreases to about a few percent at the edge of the star. But once there is a superfluid, the both electron and lepton fraction increases dramatically towards the surface of the star. This is simply obtained by distributing a fixed number of total leptons 4 times 10 to the 56, corresponding to about a quarter. YR average across the star equal to about a quarter throughout the star by the superfluid. In addition to this transport, there is a auxiliary effect coming from the flattened chemical potential profile. So akin to the thermal effect of the voltage difference across resistors, this large gradient of lepton number chemical potential in the standard scenario drives generates heat, and that is one major source that can drive the temperature of a proto-neutron star to about 50 or 60 MeV. Now, in the absence of such large gradient, we expect that the heating will be stressed so that the maximum temperature attainable in the at the center of the star could also be lowered. But to actually know what the thermal profile is, one really need to do a fully consistent simulation, taking account of feedback effects. And that is something that we're in the process of developing. In addition to the net thermal effect, we also expect the thermal conductivity to be reduced in the presence of a superfluid. This is because the neutrinos dominate the heat transport in the standard scenario, since charged leptons and baryons are tightly coupled and they do not have a appreciable mean-free path. But in the presence of a superfluid, the Gaussian mode strongly couples to the neutrinos, which allows for this Cherenkov radiation to proceed. And this reaction drastically reduces the neutrino mean-free path. So on the right, we have plotted the mean-free path of neutrinos due to the standard weak interaction neutral current reactions, which predicts mean-free path on the order of meters at about saturation density and at a temperature of 20 MeV. But in the presence of superfluid, we find that the Cherenkov radiation brings this down almost 5 or 6 orders of magnitude. And the effects are similar to both nu E's and nu E bars. Since in this study, we only focus on the couplings to the electron favor, so there isn't reductions to the nu and tau as I'm showing. But those effects can be easily included, and once these couplings are turned on, we expect those flavor, the transport due to those neutrinos can also be suppressed. Finally, one may ask, what are some of the observable signatures? I have talked about how they can change the composition, the transport, but most important is how we can know if there is a superfluid inside the star. Certainly, those effects on the transport property will indirectly impact the neutrino decoupling property. But can the superfluid have a more direct, leave a more direct influence on the neutrino signal? So what we find is that there probably won't be able to the superfluid won't leave a direct imprint because the neutrinos are so tightly coupled in the superfluid, the decoupling must occur outside the condensed region. Even in cases where the superfluid edge might extend to very large radii, say about 15 kilometers or even 20, we find that because the lepton number fraction, the gradient of lepton number fraction is very steep, the flux of neutrinos expected from such a large superfluid condensed region will be very large early on. So the superfluid is likely to recede to a smaller radii on a very short time scale, probably milliseconds to hundreds of milliseconds. But that doesn't mean that the neutrino decoupling is not affected. We still have the scalar degrees of freedom outside the condensed region, and as one might expect, any weak scale interactions could have a strong impact on the decoupling, and that is indeed what we found for part of the parameter space. So in this exploratory work, we only focus on this leading order effect, that is the on-shell production of the phy's. And to actually model the neutrino interaction outside the decoupling region, we adopted this very simple geometric model called the neutrino Bob model, in which we assume that all neutrinos decouple at a single radii are new, and that the spectrum of neutrino at the decoupling surface is a perfect black body. I want to emphasize that neither of these assumptions are perfectly well, as revealed by simulations, even assuming the standard neutrino physics. But this is nonetheless a good starting point for orders of magnitude estimate. So in this model, there is a maximum. So neutrinos outside the decoupling surface at a given radius can only collide with a neutrino can only collide with a neutrino with a the neutrinos are form a beam at each point, and there's a maximum angle of there's an upper bound on the opening angle of that cone, and this restricts the phase space of these reactions, which allows us to get an estimate on the reaction rates at each distance from the star. Now, using that neutrino reaction mean-free path, we can adopt the standard decoupling criterion by setting the decoupling by setting the optical depth to about 2/3. And this would give us a relation between the decoupling radius R nu to the temperature at the decoupling surface T nu. We also fix the luminosity to be around 10 times 51 ergs per second, as suggested by 1987, and this allows us to draw contours of constant T nu on the coupling and M5 parameter space. So Bayesian analysis of those 20 neutrinos from 1987 sort of disfavors a decoupling temperature less than about 3 MeV, or in this case, R nu that is too or a R nu that is too small. So we can sort of put a bound on doing this just from the neutrino signal from 1987, and that is to say the region, this color region is disfavored by the neutrino signal. And for references, I also shown the weak scale, assuming effective Ford-Fermi coupling, and as you can see, even a weak scale can be ruled out for a mediator light by about 30 MeV. So for those even stronger interactions, say 1,000,000 times G Fermi, and that will be safely ruled out for light mediators. In this analysis, the decoupling between the nu ES and nu E bars are very similar, and that could have very important effects on nucleosynthesis, since this will lower the neutron to proton ratio. Although I have presented our speculations of what could happen for the neutrino decoupling, but I would like to emphasize that all this cannot be said for sure before a fully self-consistent simulations has been performed for proto-neutron star evolution in the presence of a superfluid. I already hit the half-hour mark, so I will quickly conclude my talk. So there is very interesting phenomenology for new weak scale neutrino interactions, but various sources have pointed that strong neutrino self-interactions are probably not very likely, at least for the electron and muon failures. And there are also constraints on the tau flavors, but not as strong. So there might still be some hope in that channel. And so and secondly, the core collapse supernova has been a very powerful laboratory, and they still are. At this stage, maybe some immediate effect that has been overlooked could have important consequences for dark matter phenomenology. In this project, we find that the dark lepton superfluid can drastically change the composition and the transport properties. And with the help of self-consistent simulations, we hope to identify reliable observable signatures from the neutrino signals to hopefully put a constraint or find new effects due to the superfluid phase. And this is the one of the ongoing work. And those models can easily, and there are lots of related work that one can take upon. For instance, the couplings involving other flavors and also those flavor violating off-diagonal couplings. And those large production rates that I provided also suggest that the superfluid could also form even before, even during the core collapse phase, and even if there isn't a superfluid phase during core collapse, the phase which mediates strong neutrino self-interaction could still have important consequences on the dynamics of the core collapse, as already hinted by previous works in the literature. And also there still needs to be a fully self-consistent study of BBN of such light mediators. So that will be the end of my talk. And thank you for your attention. I will be happy to take questions.
Thank you very much, Dake, for this very nice talk. So we have a question from Baha.
Hi, very interesting talk. Of course, these topics are very interesting. They have to be explored well. I have a question about one of your slides. You, of course, mentioned that if you try to get such an interaction from the standard model fields, it's dimension 6. And then you mentioned that it is order of 1, the coefficient. Well, other dimension 6 operators that we know, like that violate time reversal or CP invariance, we know from the electric dipole moments that the energy scale is very small, very large. So it's suppressed quite a bit, those interactions. Why, in this case, even though energy scale is very large, the whole combination is order of 1. Is there an argument for this?
Purely from model building point of view. So no experimental inputs.
Well, but we have limits from the electric dipole moment of particles for what that thing is, energy scale is.
But that breaks CP. This is completely different.
Why? It's dimension 6.
But who cares? It doesn't break CP symmetry.
I know it doesn't, but this is a dimension 6 operator, like the CP
But it can be,
breaking up.
be completely different.
You're saying that it could be different energy scales?
Oh, sure.
Okay, well then.
Or it could be different couplings with the same energy suppression, but if CP is an approximate symmetry, you suppress the numerator, for example.
Right, but that requires an additional.
Yeah, but can I see many raised hands, but my question is very related to Baha. So if you look at that relation, as it's written, like G, absolute value of G, F alpha beta V square over lambda square. So it looks like to make G order 1, you need, I'm trying to understand, I have the same issue as Baha. Lambda has to be very close to the weak scale, to V.
Yes.
Right, so is that the class of models you're looking at?
Yes, I mean, there can be models that allows lambda that is close to the electroweak scale. Yes.
Okay, thank you. Yeah.
Thanks. We can come back maybe to it during discussion if people want. And next question, maybe from Gail, if you can unmute yourself.
You are muted, Gail.
We still can't hear you. I don't.
Yeah, sorry, I cannot hear.
How about now?
Yes.
Okay. Yes, I need a new computer, I think. Okay, so my question is about, so I wanted to thank you, first of all, for that's one of the things I said when I was muted, to thank you for the very nice talk. And then I have a question about your analysis at the end. When you look at you decide where the neutrinos decouple, you look for the optical depth of 2/3. And are you doing this separately for neutrinos and antineutrinos? And when you determine the decoupling surface, which I think you're making spherical because you're in the bulb model, is that right? So if you look at the difference between the neutrino coupling and the antineutrino decoupling surface, when you add in new interactions, is that the difference between those, like the fractional difference, is it changing? Or is it stay mostly the same?
Oh, yeah. So, right. So if the decoupling is dominated by the weakening action, yes. I mean the nu E and nu E bar will be different. But in this model, we consider statistically. I mean, it's we sort of expect the decoupling to occur at the chemical potential where the chemical potential vanishes. So really, there isn't a so really the nu E and nu E bar are decoupling are basically identical. So there really isn't a difference in the two.
So it is changing. They're different in the weak interaction, but in this model they're identical.
Right. Yes.
Okay. Thanks.
Yeah, but again, that's probably due to the assumptions, the simplifications we make, and yeah, we really need to do a simulation to actually know that for sure.
Okay. Thank you.
Thank you. We have another question from Pedro. Can you unmute yourself and ask?
Hi, Dake. Thank you for the great talk. I was wondering if the timescales here, what happens after the proto-neutron star kind of settles towards some equilibrium configuration? Is it possible that its equilibrium properties are affected by density of scalar particles it inherits, I guess, from the supernova?
Right, so I lost you for a few seconds, but I guess your question is basically whether the superfluid can survive the early evolution and
yes.
Yeah, okay. Yeah. So we find that because the gold zone mode is quite steep. So if I just calculate the grand potential, it's actually large at zero temperature. The grand potential, including the superfluid, will be larger than that of the standard scenario. So we expect that the actual ground state at zero temperature will be the standard mode of physics.
Okay, thank you.
Okay. Thank you. Next question, Susan. Can you unmute yourself?
Thank you very much. I have a simple question. Unfortunately, I at a conflict couldn't hear all of your really nice talk, but I have a question in regards to, I guess, thinking about how supernovae may proceed in the advent of this, I guess, lepton condensate idea, or the idea that you have at least suitably strong couplings between this scalar and neutrinos. In particular, it strikes me that as a result, that you can hold, when you have the initial collapse to form, to actually have a supernova, that your neutrinos might not be as efficient as carrying away energy in the collapse, in the presence of this exotic scenario than otherwise. And so just looking forward, if we look at the final neutron stars that might emerge from such a scenario, would they not, as a population, be rather, how to say, could you expect them to be intrinsically hotter? I don't know how well we expect or what we expect the typical neutron star temperatures to be. But if you have a scenario where the neutrinos do not carry away energy as efficiently, maybe ultimately you end up with hotter neutron stars. I was wondering if I'm possibly you talked about some of this or maybe not, but maybe you could just talk about some of the ideas and implications. That'd be really interesting.
Yeah, definitely. Yeah, so that's part of the ongoing work, and actually there are earlier works, I think mostly by George Ford and his collaborators, looking various Maron models and how they and how these scalar particles can affect quark collapse. I think one of the potential signatures they have identified is that indeed the quark collapse could be probably halted because the coupling of electrons to the other flavors, those off-diagonal couplings could basically those will remove those high energy neutrinos, so the neutrino chemical potential will be lowered. And that will enhance electron capture because the Pauli blocking is removed. And using simulation, they find that there will be more entropy production, so one of the consequences, so it will probably be hotter, and the time scale for the quark collapse will be probably longer, and it's not even clear if the shock wave will be generated at sufficiently high density to explode the star. So I think there are several ideas in that direction, but right. So I haven't studied those in detail. Does that answers your question?
I think that's very interesting. Thank you.
Thanks. And we also have a question from Yang Bai. If you could unmute yourself, just go ahead.
Thanks for the interesting talk. I have a question about the effective potential. So you're down the, I don't know which slide now. So this potential. So first the question is, this is zero temperature potential, but I thought that the temperature is hot, so there should be finite temperature modification for this potential. Will that change the calculation you perform here?
So the thermal loops, those have been worked out by others, those will involve the renormalizations of the couplings of the masses. And since we're mostly interested in the phenomenology, so instead of fixing the couplings themselves, we try to fix observables such as the condensate amplitude and stuff. So these parameters, if taken to be the renormalized value, I think so in our calculation we're treating those parameters as renormalized values, and the thermal effect is not is implicitly included in our calculation.
That's because you do have this cortical coupling, right? This little lambda. So that even by that coupling by itself, there should be little lambda t square phi star phi term, and I just trying to say inevitably you should have some t square contribution to the mass. I don't know whether it's larger than the existing terms or not. Otherwise, you could have some parameter space which you don't have the condensation. Right.
Yes. Yeah. So we treated. Well. Yeah. So that. Yeah. So that effect has not been included, but the condensation is not always guaranteed. Okay.
I see. Another related question, which is, I think you did assume the interaction is strong enough such that the chemical is thermally equilibrium or chemically equilibrium, right? So this condition, I'm just wondering, suppose for some company a little bit weak, suppose you don't have the chemical equilibrium for the 5 particle with electron and neutrino, for example. Because if you don't have that, then if I look at this effective potential, the mu-phi square term could be coupling dependent. Because so far you assume such that you just only care about the chemical potential, right? But otherwise you could have some coupling dependent for this effective mass term for phi star phi. So then again, there will be depends on the coupling strength. You could have some cases you could have a condensation. Some cases you don't have condensation. I just wondering, like, is that something you guys planning to also study or not?
So I think there are probably two separate parts, so sort of separate parts. Yeah. So in those sort of weakly, well, moderately coupled region, yeah. So we actually need to solve the Boltzmann equations to figure out the spectrum of the particles. Yeah, and certainly this is all the zeroth order approximation. Everything is in perfect equilibrium. Yeah, but then so to capture those, we will have to do a Boltzmann. But even like without considering those effects or the thermal corrections to the quartic potential, I mean, we still admit regions where we have condensate and regions we don't. I mean, that's work out at what they call the one loop level, I think, in the thermal field theory. So that can be incorporated even without those effects, and we actually incorporate those.
Okay, thank you.
Okay. Thanks for the question.
Thank you. Susan, do you have another question?
Oh, I'm sorry. I forgot to lower my hand.
Okay.
Sorry.
No problem. Yes, then I don't see any more raised hands. So thank you, Dake, again for this very interesting talk. And if someone wants to stay and discuss, we will hang out here a couple of minutes with Dake. But otherwise, see you